Okay, so we're going to start talking about the gas laws, temperature, pressure, and Dalton's law. Do some conversions, easy peasy stuff. There's several variables we talk about when we're looking at the gas laws. We started investigating pressure last week and then volume and temperature. So those are going to be our first four that we look at: temperature, volume, pressure, and these all have units that we need to pay attention to. And then, of course, our favorite is the mole. Let's start with temperature first. When it comes to temperature, we've learned this before. It's the measure of the average kinetic energy of the particles. That kinetic molecular theory we started investigating. For any gas law equation, you must have the temperature in Kelvin, and we're going to learn how to convert Celsius to Kelvin right now. Kelvin can never be a negative number because it's based on absolute zero. It is the absolute scale where at 0 Kelvin all matter stops moving. Remember, the Celsius scale is an invented temperature scale by humans based on the substance we knew, water, at its freezing and boiling point. So, and this is just saying, back to kinetic molecular theory, we know our gas particles will slow down as temperature decreases, and they would theoretically stop once we reach 0 Kelvin. But we have not yet reached that temperature yet. We'll see. We'll see what happens when we do. Okay, so let's talk about standard temperature. So you're going to start seeing this term, standard temperature and pressure. Standard temperature is 273 Kelvin, or 0 degrees Celsius. We're going to go through and convert from Celsius to Kelvin, because in the lab we don't measure Kelvin. Our thermometers, they measure temperature in Celsius, so we have to convert to Kelvin. And the way we do that is, if you were to go into the lab, you measure your Celsius temperature, you would add 273 to it to get your Kelvin temperature. But reverse that, and you could find the Celsius temperature by subtracting 273 from your Kelvin temperature. Alrighty, let's go ahead and do some problems with our temperatures. So let's say we went into the lab, room temperature ended up measuring at 25 degrees Celsius. How would you convert to Kelvin? You would simply take that 25, add 273 to it, and your answer would be 298 Kelvin. And notice there is a space between the number and the unit. That is standard practice. Alrighty, what about if you have a problem, it's in Kelvin, and then I ask you to convert back to Celsius? Just do the opposite. 278 minus 273, and you would see that that's a 5 degrees Celsius. And remember, we are subtracting here, so we're not limited by number of digits, we're limited by number of decimal places for our sig figs. That's why it is simply just 5. Let's do another Celsius to Kelvin. You can pause the video right now if you'd like and try this on your own, and then check your work. All right, let's go ahead. So you take that negative 15, add 273 to it, and you see that you have a Kelvin temperature of 258. Let's take another one where we're Kelvin to Celsius. Again, you could pause the video right now and try it on your own. Take that Celsius temperature or Kelvin temperature, add 273 to it, and you get, subtract 273, and you get negative 273 Kelvin. So going from Celsius to Kelvin is pretty straightforward. Let's go ahead and talk about gas pressure, some pressure conversion in Dalton's law, and then we're done. So for gas pressure, again, back to KMT, they're always moving and colliding, and every collision exerts a force on the container, and that force is the pressure. So the more collisions, the higher the pressure. And pressure is defined as force per unit area. And this is simply saying that we take gas pressure as a combination of all the molecules, no matter type. Helium, argon, oxygen, doesn't matter what type, all of them together, because they're all colliding on the container, and that gives you gas pressure. And we measure gas pressure with a barometer, and Mr. Torricelli was investigating that. So this is your standard barometer right here. This is how they first came up with it. They took a tube of mercury, it was full, they inverted it and put the opening under a liquid mercury, and then removed the top. And they noticed the mercury didn't fall and empty into the dish as they were expecting. Instead, it created a vacuum, and then we have the mercury just sitting there. And what they found was at sea level, no matter where, it was always a specific height, 760 millimeters high. And so what is essentially happening here is we started seeing this last week, how strong atmospheric pressure is. It's pushing down on the surface of the liquid in the dish, and in response, the pushing up on the mercury. And the weight of the mercury and the push up from the atmosphere are in equilibrium when it is 760 millimeters high. So we actually have a unit for pressure using distance. So one of the only times you see that. It's 760 millimeters of mercury is a pressure. This is a manometer. We're going to just skip right past that. All right, let's talk about the units that you're possibly going to see. We have an atmosphere, which is generally defined as what we exist in. Millimeters of mercury from the barometer, so mmHg. And since Mr. Torricelli was doing the experiments, he gets his own unit called a torr to represent pressure. We also have pounds per unit or inches squared, but we don't deal with that in chemistry. And then our SI unit is the Pascal for another gentleman who was looking at this stuff. Okay, so let's go ahead and keep on going. So we're going to go ahead and do some examples, but first let's know our units. So we exist in this atmosphere. There are other units, the PSI, the Pascal. How do we convert between them? So our equalities, 1 atmosphere is 760 millimeters high to represent the length, the height of that column, which is also a 760 torr, which is 14.7 psi. You rarely use that in chemistry. 101.3 kilopascals, or 1.013 times 10 to the 5th pascals. We tend to use kilopascals to get rid of that big scientific notation number. All right, let's do our first example. 923 millimeters of mercury is how many atmospheres? So what you'll do is you'll go up here and take a look. We want a millimeter of mercury, so we'll go to this one, to atmospheres, and just have to wisely place your conversion factor so that way we get that millimeter of mercury to cancel out. So start with your given, and then you're going to go ahead and put in your conversion factor, and I've got those from up here. And we're doing this because we want to go ahead and we're going to cancel out that millimeter of mercury, since we put it on the bottom, divide through, and you will get 1.218 ppm. Easy peasy. 3 sig figs, because our measurement has 3 significant digits. Please, please, please don't use the 760. That's not your measurement, so you go by your measurement on sig figs. Let's do the second example, and you can pause the video and try it on your own first. So we're going to go ahead and start with our given, which is the kPa, and I'm going to look up here. kPa is the 101.3 kilopascals, so it's right here. And I'm going to go to a torr, so I'm going to pay attention to this one. Alrighty, so I'm going to go ahead and I'm going to put those two numbers as my conversion factor, putting kPa on the bottom because I want it to cancel out and get to the Torricelli. And when you do that, you're going to multiply 97.8 by the 760 torr, then divide by 101.3, giving you 3 sig figs because our measurement has 3 to give you 733 torr. And then our last one, and feel free to pause again, we're going to start with 0.72 atm. We're going to go from atmospheres to pascals, the big one. So put that in there. And I'm putting atmospheres on the bottom, as you are all probably aware now, because I want those atmospheres to go away. Alrighty. And 2 sig figs for this answer because of the 0.72, and you get 73,000 pascals. Don't be scared of numbers. It is a big number, but it's the right number. Alrighty. Let's go ahead and talk about Dalton's law, and then this video is done. So Dalton was studying partial pressures. The whole idea behind this is that you can have a mixture of gases, but each gas has its own individual pressure. For example, in the atmosphere, we have oxygen, carbon dioxide, nitrogen, all sorts of stuff. Well, the oxygen has its own partial pressure. The nitrogen has its own partial pressure. And when you add them up, you can get the total pressure in that system. And it's an easy peasy formula. You just take, oops, there we go. So the pressure total in whatever system you're looking at, you're just going to add them up. So the pressure of gas 1, pressure of gas 2, plus the pressure of gas 3 ends up being your total pressure, depending on how many you have in that container. So this is an example. We have atmospheric pressure. Well, where does the 101.3 kilopascals come from? We have oxygen at 20.9, nitrogen, argon, water, CO2. These are your major components. When you add them all up, that adds up to 101.3. So we have individual pressures adding up to combined pressure. All right, we're going to do one example, and then we are finished with this video. So what is the pressure of a mixture of helium, nitrogen, and oxygen if their partial pressures are 720 millimeters of mercury, 210, and 364 millimeters of mercury, respectively? So we have three gases, three pressures. All we have to do is realize that the combination of all those three, add them up, that's your total pressure. So I'm going to take PT, which means total pressure. It's going to be the sum of the pressure from the helium, pressure from the nitrogen, and pressure from the oxygen. And just plugging the numbers in correctly, 720 plus 210 plus 364. Now we're adding, so it's digits or decimals, decimal places. So we're going to end up at the ones place, 1,294 millimeters of mercury. So that's above atmospheric pressure. And that is it. Thank you for watching. I hope you completed your notes so we can get right down to business on Monday with some fun activities.